We're now going to talk about removable discontinuities. So as it turns out, there's two ways that a function can fail to be continuous, and we can kind of think of one of the two ways as being kind of a bad continuity. And the reason it's bad is that we can't do anything about it. It's not removable. And then there's other types of continuity that aren't as bad, and they can be fixed, and you can actually remove the discontinuity. And so let me show you what these two types of continuity are and what makes them different here. So one type of continuity might be something like this, where you have a graph, and then maybe it makes a jump here. Maybe it's something like that. Okay, and then here at C, the function is not continuous at C. It makes this jump. Okay, and what makes it not continuous here is that the limit does not exist. So it's not continuous because the limit as x approaches C does not exist. And that's what makes it discontinuous. Okay? But you could have a situation like this where maybe the limit does exist. Maybe it's something like this, and then you know, at C here it's actually equal to some other point, right? And then it kind of goes on from there. And so at C, the limit actually exists. It actually is going to the same point, but f of C does not equal the limit here. So the limit here as x approaches C, so the limit exists, no problem there, right? It exists, but the limit as x approaches C of f of x, that does not equal f of C. Okay? Or maybe f of C doesn't even exist. Maybe there's just a hole there and it doesn't even exist. Or it could be that the two don't equal one another. Okay? Well, notice here that this could easily be fixed, right? All I need to do is redefine f at C to equal the limit as x approaches C. Okay, and in that sense, I can remove the discontinuity. So this is a removable discontinuity. Okay, and it's removable because I can redefine f at C at that one single point and plug in the hole so that f is now continuous at C. Over here, though, I cannot do that, right? I can't redefine f at C and then have it be continuous because the limit does not exist. Okay, and so we would say that this is a non-removable discontinuity. So this is a more serious kind of discontinuity. It's non-removable. I can't redefine f at C and then remove the discontinuity. So what makes it a more serious discontinuity is that the limit as x approaches C of f of x does not exist. Okay, if the limit does not exist, it's a non-removable discontinuity. That's the bad kind of discontinuity, or the more serious kind that you can't fix just by redefining f at C. But if the limit does exist, but it fails to be continuous because that limit doesn't equal f at C, or maybe f isn't defined at C, that's not as serious, because if the limit exists, I could just redefine f at that one point, pick up that dot, plug in the hole, and then it would be continuous at that point. Okay? So let's show a couple examples here. And I like to use the following one to illustrate this. because it has both a non-removable and a removable discontinuity. Okay, so let's consider the function, we'll say x minus 2 over x squared minus 4. Okay, and by now you're probably already getting used to the fact that sometimes you can factor these, right? And you can cancel out a problem spot where you would normally have a vertical asymptote, but if you can cancel it out, you don't have a vertical asymptote anymore at, in this case, at 2, but this will still have a vertical asymptote at -2. Okay, so the behavior of this behaves just like this. Okay, and so I can actually graph this. This is like the 1 over x shifted over to the negative side two places. So this is -2. This would be the vertical asymptote, and this would be like y equals this would be like y equals 1 over x shifted over, and let's say this is 1. So at 2, this would have a hole here at 1/4. So this would be like something that goes down, and then it has this hole, and then it continues to go down, and then it would look like this. So at 2, the limit would exist. So the limit as x approaches 2 of x minus 2 over x squared minus 4, this actually exists, because this is actually equal to the limit as x approaches 2 of 1 over x plus 2, and now I can just plug it in and I would get 1/4. So in this case the limit exists, okay, but the function is undefined there. You have a hole in that spot. But since the limit exists, I can fix that by defining this function at 2 to be x at 2 to be 1/4. So in other words, we could use like a piecewise function, right? So it would look something like this. This would be x minus 2 over x squared minus 4. And this would be for x not equal to 2. And then I'm going to define it to be 1/4 for x equals 2. This function, defined in this way, this down here is filling in that hole, right? And so this is actually continuous. Continuous for all x, okay, from -infinity to infinity. Oh, no, sorry. Let me just say, not for all x, but for x equals 2. So this is continuous at x equals 2. This isn't continuous. I'm just going to erase that. This isn't continuous, however, for all x, because here at -2, the limit as x goes to -2 of x minus 2 over x squared minus 4 does not exist. It's actually going to infinity. Infinity here, -infinity there, but it doesn't equal a finite value. And so there's no way to remove this discontinuity. So this is a non-removable discontinuity. Okay, a non-removable discontinuity. So this is a function that has a non-removable discontinuity and a removable discontinuity. And this is the way that we would remove it, by redefining the function at the place where it's discontinuous, but the limit does exist, and we redefine it to be equal to the limit of the function at that point. So let's try one more. If I had f of x is equal to sine of x over x, and we can see that the function's not defined at 0, okay? But this was our function that had the special limit. Limit as x goes to 0 of sine of x over x was just equal to 1. So the limit does exist. And so if you were to actually look at this function, it's kind of like, it kind of goes down and it gets smaller and smaller. I'm not drawing it right, but these get smaller and smaller. But here at 0, it has a hole. But the limit does exist, right? So this is this would be the only place where it's discontinuous, but this is a removable discontinuity. And I could remove it by redefining f of x as follows. I would let it be equal to sine of x over x for x not equal to 0, but then I'll let it be 1 for x is equal to 0. And in this case, we're kind of plugging in that hole, right? And the function is continuous now over the whole domain, okay? So that's the idea of removable, non-removable discontinuities. And so the removable ones are the ones where the limit exists, but maybe it's not defined there, or it's defined to be something other than what the limit is. And you can remove it by redefining x at c. But then the non-removable ones are the ones where the limit doesn't even exist, and there's no way to fix that. It's, what is it, irremediable, or you can't remediate it, or whatever. It's more serious, and it can't be fixed just by redefining the function at c.